Hey everyone! Before we dive into the world of coordination chemistry, let's take a look at our roadmap for today. By the end of these sessions, we aim to achieve 5 key objectives. First, we will apply our knowledge of electrons configurations, specifically for transition metals, which are the heart of these compounds. From there, we will dive into ligand structures to understand how they interact with those metals. Moving into the practical side, we will learn how to properly name these complex ions and compounds using IUPAC conventions. We will also explore the 3D world by determining their geometry, whether they are octahedral, tetrahedral, or square planar. Finally, we will wrap up by identifying the different types of isomerisms that gives these compounds their unique properties. Now, let's start with the basic. What exactly is coordination compound? As you can see on the screen, these compounds mostly involve transition metals. A coordination compound is typically made of two main parts, a complex ion and a counter ion, which can be either a cation or an anion to balance the overall charge. Take a look at the example here, CONH35Cl. The part inside the brackets is our complex ion. If you look at the diagram, you will see a central metal atom surrounded by non-metal atoms of groups called ligands. The ligands donates two or more electrons into the vacant d orbital of the metals. This specific type of sharing called dative or coordinate bond. It's this unique bonding that gives coordination chemistry its names and its fascinating variety of colors and magnetic properties. Okay, let's zoom in on the complex ion itself. As you can see in the chemical formula on the screen, a complex ion is a larger, charged species. It forms when ligands, the group shown here in the parenthesis, binds to a central atom, a central metal ion. What's happening at the molecular level? The ligands are acting as donors. They donate lone pairs of electrons to the metal ions, creating what we call dative covalent bonds. It is important to remember that these complex ions aren't just flat or random shapes. They have different geometries depending on how many ligands are attached. Furthermore, these ions contribute to the isomerisms and the specific chemical behavior of the entire coordination compound.
Ligands are Lewis-based, which means they donate a pair of electrons to the metal ion. The metal ion acts as Lewis acid, accepting the electron pair to form a coordinate bond. Ligands can be natural molecules such as H2O or NH3, or negatively charged ions such as Al. There are three main types of ligand. First, monodentate ligand, which donate only one atom to the metal, for example, chloride. Second, bidentate ligand, which donate two atoms such as En. Third, polydentate ligand, which donate more than two atoms, for example, EDTA, which is hexadentate. The coordination number is the number of donor atoms directly bonded to the central metal ion. It is important to note that the coordination number depends on the number of donor atoms, not the number of ligands. Okay, in this example, the ligands bonded to the cobalt are 5 ammonia molecules and 1 chloride ion. Each ammonia donates 1 nitrogen atom and chloride donates 1 atom. Therefore, the coordination number is 6. EDTA is a hexadentate ligand, meaning it donates 6 donor atoms to the metal. Once EDTA binds to the metal ion, no additional ligands can attack. Thus, the coordination number is also 6. Okay, the coordination number also determines the shape or geometry of the complex. If the coordination number is 2, the geometry is linear. If the coordination number is 4, the geometry can be tetrahedral or square planar. If the coordination number is 6, the geometry is octahedral. Okay, for example, for copper complex, CuH2O2 2 plus and CuEn 2 plus have coordination number of 2, so they are linear. CuH2O4 2 plus and CuEn 2 2 plus have a coordination number of 4, so there may be a tetrahedral or a square planar. And lastly, CuH2O6 2 plus and CuEn 2 2 plus have a coordination number of 6, which give an octahedral structure. Okay, for naming coordination compound, there are several basic rules that we need to follow. First, the cation is named before the anion. If the complex ion is negatively charged, the metal name ends with ATE. Second, ligands are named before the metal ion, and they are arranged in alphabetical order, ignoring any prefix. Third, we use prefix such as di, tri, tetra, penta, and hexa to indicate the number of ligands present. Lastly, for the transition metal, the oxidation number of the metal is written in a Roman numeral in brackets. Prefix such as di, tri, tetra, and penta are used to show the number of ligands. However, these prefixes are ignored when arranging ligands alphabetically. For polydentate ligands such as ethyl and diamine, we use special prefixes like bis, tris, and tetrakis instead of di or tri. Okay, let us look at this example. KCrCl2En2. First, potassium is the counter ion, so it named first. Next, we determine the oxidation number of chromium Chloride has charge of -1, ethyl and diamine is neutral, and the overall charge of the complex is -1. Therefore, the oxidation state of chromium is +1. The coordination number is 6 because chromium is bonded to 2 chloride ions and 2 bidentate ethyl and diamine ligands. The geometry of this complex is octahedral. The final name is potassium dichloro bis ethyl and diamine chromate 1 ion.
Now, I will present structure and isomerisms. First, coordination number can determine the shape. So, coordination number 2 give linear shape. Coordination number 4 can be tetrahedral or square planar. And lastly, coordination number 6 is octahedral. So, we need to remember that in coordination compound, there is only 3 coordination number, which is 2, 4, and 6. So, coordination number 4 give 2 shapes, either tetrahedral or square planar. So, here is how to identify each shape. So, for square planar happens with D8 metals, which is there are 8 electrons at the d orbitals like nickel 2+, platinum 2+, especially with strong field ligands like ammonia or cyanides. That's square planar. For tetrahedral is everything else than the one that I listed as square planar, like cobalt 2+ or copper chloride 4 2- with weak ligands like chloride. So, for a quick tips to remember, platinum or nickel with strong ligands equals to square planar. Then the others, everything else is tetrahedral. So, these are the 4 coordinated complex ions and 6 coordinated complex ions. The diagrams we can see the tetrahedral and square planar arrangements. Tetrahedral arrangements, we can see cuprum is the metal while Cl is the ligands, which is weak ligands. That's why it gives tetrahedral arrangements. So, for the square planar arrangements, platinum is the metal while NH3 and Cl is the ligands. NH3 is strong ligands, that's why it gives square planar arrangements. Like the tips I just said, platinum and nickel with strong ligands will give square planar arrangements. Next, coordination number 6 always give octahedral geometry with 6 ligands around the metal. 4 in the equator plane and 2 is at the above and below. In the example, we can see ferrum is the metals, so it is in the center. So there are 2 H2O, which is each one is at the above and below, others at the equator plane. That's why it gave octahedral arrangement. Now, we will get into the isomerism. Isomers have the same formula but different arrangements. There are 2 main types, structural isomers and stereoisomers. Structural isomers have different connections between atoms, while stereoisomers have the same connections between atoms but different shapes in space. There are 4 kinds of structural isomers, which is hydrate, ionizations, linkage, and coordination sphere. For stereoisomers, there are geometry and optical. Starting with structural isomers, hydrate isomers move water molecules in and out of the coordination sphere. It means they have the same composition but differ in the number of water molecules. As in the diagram, we can see chromium hexaaqua chloride 3 shows that all of the water molecules is in the coordination sphere. While the chromium pentaaqua chlorochlorides, one of the water molecules is out of the coordination sphere. Chromium hexaaqua chloride 3 is blue, while chromium pentaaqua chloride dihydrate is green. So, the different colors between them prove that they are isomers. Next, ionization isomers. They swap anions between the coordination sphere and counter ions. As in the diagram, cobalt pentaamine bromo sulfate 4, the anions is bromo and sulfate 4. So, sulfate 4 is at the counter ions, while bromo is in the coordination sphere. For the next diagram, cobalt pentaamine sulfate bromides, which is bromide is the counter ions and the coordination sphere, there is pentaamine sulfates, which they exchange. So, that's the ionization and hydrate isomers. The next structural isomers is linkage isomers. Linkage isomers use the same ligands but connect through different atoms. There are only 3 common types of it, which is the first one is nitrate. It can bind through nitrogen as nitro or through oxygen as nitroto. The second one is thiocyanate. It binds through sulfur as thiocyanato or through nitrogen as isothiocyanato. The third one, which is the last one, is cyanide. It binds through carbon as cyano or through nitrogen as isocyano. For each type of it, both of them have the same formula, but it gives different colors and reactivity because different atoms touch the metal center. In the diagram, as in the examples, it shows the example for nitrate, which the first one show it binds through nitrogens and the next one show that it binds through oxygen. So for the next one, which is the last for structural isomers, is coordination isomers. Coordination isomers have 2 different metals that exchange ligands. It means the coordination compounds having the same composition but occur through exchange of ligands between complex ions in the same coordination compound. which is in the example cobalt hexamine 3 plus with chromium triooxalate 3 minus can swap. So the result will be chromium hexaamines and cobalt triooxalate. The metals trade ligand sets.
Okay, for the next part, I will explain stereoisomerism in coordination compound. Stereoisomerism means compound with the same connectivity but different spatial arrangement. There are two types. First is geometrical isomerism, second is optical isomerism. Okay, first I will explain to you about geometrical isomerism. Geometrical isomerism is about where the ligand are located. Stereoisomerism that cannot be converted without breaking a chemical bond and have a different color, melting point and chemical reactivity. There are two main terms. First is cis, second is trans. Cis is the same ligand are next to each other, but trans is same ligand are opposite to each other, and this is usually happen to square planar and octahedral. Alright, for example, in complex for square planar, we have diamine dichloride platinum 2. If the two chloride ligand are beside each other, it is cis. But if two chloride ligand are opposite, it is trans. Then, example for octahedral, we have tetraamine diaqua cobalt 2 ion. If the two water ligand are beside each other, it is cis. But if the water ligand are opposite, it is trans. Even though the same formula, the arrangement is different. Okay, other than that, we move to optical isomerism. Optical isomerism is about coordination compound that are mirror image and non-superimposable to each other. If a molecule and its mirror image cannot be placed on top of each other, it is called an optical isomer. In coordination compound, optical isomerism usually happen when we have a bidentate ligand such as ethylene diamine. Okay, for example, we have a cis dichlorobis ethylene diamine cobalt 3 ion. This complex show optical isomerism because its mirror image non-superimposable. But for trans dichlorobis ethylene diamine cobalt 3 ion, it is not optically active because it has a plane of symmetry. So its mirror image is superimposable.
To wrap everything up, let's revisit the core concept we have covered today. First, we have established that coordination compounds are built around central metal ion bonded to ligands through coordinate bonds. We have seen that complex ions are the most critical parts of these compounds, heavily influencing their physical and chemical properties. Crucially, the electron configurations of those transition metals, combined with the structure of ligands, is what dictates the coordination number, the geometry, and the type of isomerism we observe. Ultimately, understanding this coordination compound is the key to explaining the complex structure and fascinating behaviors we see in inorganic chemistry. Thank you for your attention.